All right, so now we have to kind of step back from the fun stuff and really dig into the concept of limits because it's important. So I just have this function I made up that I think serves as a pretty good demonstration of what exactly the limit is. So if you look at the graph here, this is the function f of x equals sine of x over x. And it certainly looks like there's a hole in it right at x equals 0. So if you think about it, remember sine of 0 is 0. So f of 0 is in fact undefined, and it's undefined in that kind of limity way where there is a hole there, where there is a value that the function should take on. And just by looking at the graph, it sure looks like at x equals 0, the function should be 1. So it looks like there's a limit there and that the limit is 1. If we look at a table of values, that makes it even clearer. As we approach 0 from either direction, right, from the left or from the right, it looks like these values in the this column are converging to 1 from either direction. In other words, if you had to fill in that error, you would probably put the number 1 in there, and you'd be correct. That's not proof, it's just what it looks like. So remember the way that we say that. The limit as x approaches 0 of this function is 1. So as we approach 0 from either direction, these numbers over here can be made to be arbitrarily close to the number 1, meaning if we kept zooming in and zooming in, we would just get like 0.9999999 here. We would never quite get to 1, but we could get as close as we possibly wanted. So the limit exists, and it's 1. And now I've modified it a bit. So this is a piecewise defined function. We can take functions and do whatever we want with them. So it's identical to the last function, except what we've done is when x equals 0, we've just said, okay, let's just define the function to be equal to 2 there. So you see this dot where the function just is defined. It just happens to be defined up here for some reason. So that doesn't affect the limit. So if you think about everything I just said, as x approaches 0 along the curve from either direction, the function becomes arbitrarily close to 1. Except now it jumps up and just is defined at 2. But that doesn't matter. So right, just think about those words. As x approaches 0 from either direction, the function gets arbitrarily close to 1. It doesn't get arbitrarily close to 2. It just jumps up to 2. So the point is that the limit is exactly the same. The limit doesn't care what actually happens here. All it really cares about is what happens near here. It cares about what happens to these values as x approaches 0. It doesn't care about what happens when x actually is 0. So this could be 2 or 5 or negative 100 or whatever. The limit as x approaches 0 of this weird new function is still 1. It doesn't matter what happens at 0. And think about that from the terms of this table of values too. These are all the same. And those are the ones that determine the limit. These numbers leading up to 0, near 0, are still converging to 1. They're not converging to 2, right? It just jumps up to 2 here. So giving the function a different value at that exact moment there doesn't change at all what the limit is. Okay, now I'm going to mess with it one more time. And I've just done a similar kind of thing, except at x equals 0, I've defined the function just to be 1. So what did we do there? We just filled in the hole, right? We said, okay, there should be a 1 there, and now there just is, right? So that's called what we call removable discontinuity. All we'd have to do to fix that function is just stick a point in there where the function we think should be 1 and just make it 1. So the point I want to illustrate here is that the limit is still the same. The limit is still 1. So you don't need a weird thing for there to be a limit. If a function is just continuous, I think you have some sense of what that word means. You can draw it without picking up your pencil. Then the limit still exists. It's just whatever the function is there. So the limit as x approaches 0 of this function is still 1, right? You don't need a hole there for the limit to exist. If you look at a table of values for this, you just would have a 1 here and it would just be filled in, but nothing I said about what happens to either side of that changes at all. Okay, so the limit exists if the function is either just continuous, like a normal function, or if we have what I call that kind of removable discontinuity, or a hole. If there's a hole there, then the limit is just whatever the function should be in that hole. So usually it's there. So it's more helpful for us to just look at a couple cases where the limit isn't there. There's only a couple cases where a function or a graph where we would just say the limit does not exist. So the first case is this. If you think about the function 1 over x squared. Well, you know what happens at 0. Obviously, you can't divide by 0. So that function has a big old vertical asymptote right there. Obviously, f of 0 is what we would call undefined because you can't divide by 0. But that's not a hole. It's an asymptote. And what does an asymptote do? It makes the function shoot up to infinity. So in this case, it does, in fact, shoot up to positive infinity. And you can't say that infinity is a number because it's not. So you don't say the limit is undefined. We just use the word does not exist. So on a quiz and stuff, if there's one where there is no limit, we just type DNE for short, or you can write out does not exist. It's just not there. It just doesn't apply in the case where the function shoots off to infinity. One little confusing bit of notation that you're going to see, so I have to introduce it, is you will sometimes see that the limit as x approaches 0 of this thing, some texts and teachers will say that that limit equals infinity, like that. That still doesn't mean that the limit exists. The limit has to be a finite number. So I'm sorry that that's confusing, but all this notation does is it specifies that this function in fact shoots up coming from either direction. The function shoots up to infinity rather than down to negative infinity. If it shot down like that, then you could say that, okay, the limit equals negative infinity. So you wouldn't be wrong to put that. I would never mark it wrong because I just told you about it. It's probably easiest for everybody if you just kind of ignore that. And just in the case, if there's a vertical asymptote anywhere, just say the limit doesn't exist there, because then you know you're right. Okay, second case, and this is a little weirder. So again, I just kind of constructed a weird function because it illustrates a point. This function is so absolute value of x over x. So we have a graph, but think about why this thing looks this way. If x is any positive number, like 2, 3, then the absolute value of x is just x. So if x is positive, absolute value of x over x is just 1, right? It's just the same as x over x, which is always 1. If x is any negative number, like if x were negative 2, okay, the absolute value of negative 2 is 2. So 2 over negative 2 is negative 1. So all this function is it's like, okay, if x is positive, it kicks back a 1. And if x is negative, it kicks back a negative 1. That's it. So that's why it looks like just these two straight lines that split. We have a similar thing happening at 0. The absolute value of 0 is 0, but 0 over 0 is still undefined. So the way you'll see it drawn is if this is an open dot like it is here, that means there's nothing there. If we were to say close the dot here, then that would make f of 0 be 1, but it's not in this case. F of 0 is undefined. Okay, but that doesn't really affect the limit. What affects the limit is that it's doing a different thing coming this way as it is coming this way. So So in other words, if you're coming from the left here, you have, if you were to look at a table, it's just -1, -1, -1, -1, error. If you're coming from the right, you'd have 1, 1, 1, 1, 1, 1, 1, error. So if you just were looking from this side, it would look like the limit was -1, and it would be. If you were just looking from this direction, it would look like the limit was 1. But the problem is it has to be the same thing. And I've said that before. For the limit to truly exist, it has to be the same thing coming from either direction. And since 1 does not equal -1, the limit of this function as x goes to 0 doesn't exist. Okay, so that's how you'd write that. The limit as x approaches 0 of this just does not exist, because if I were to ask you why, you would just say because 1 doesn't equal -1. And we do have words for that, a one-sided limit. So you could call it like a left-handed limit and a right-handed limit. And you would just say that those two limits aren't equal. And so therefore, that's all you have to say. It doesn't exist. Don't split the difference. Don't say because this one's 1 and this one's -1, then we split the difference and say the limit is 0. That's not how it works. It has to be the same. So intuitively, if you see an asymptote, the limit doesn't exist. If you see a break, this would be called a jump discontinuity. We'll get into different kinds of discontinuity soon, right? A place where the function just jumps from one value to another abruptly, then you just say, boom, the limit does not exist there. We do have some notation, though, for these so-called one-sided limits. So since if you're coming from the left, it's just -1s all the way down up to here, then the limit just coming this way, if you've ignored all this stuff, would exist. So that's called like a left-handed or a one-sided limit, and here's how we write it. So it's this little minus sign in superscript there. If you see the limit as x approaches 0 with a little minus equals -1, that little minus means either you can think about it as from the left or from below. Either way, it means coming this way, coming from left to right is what that little minus sign means. So that one-sided limit does exist. And the same with this, the right-handed limit, so coming from the right or coming from above would just be 1. So that one-sided limit exists as well. So we'll do a big example of this in a second. But if I were to ask you for coming this way, well, if the function was more or less continuous coming this way, then yeah, you would have a limit. And if it was continuous coming this way, then yeah, you probably would have a limit. But this, anytime you see just x approaches 0 with no little plus or minus sign, that always means coming from both directions. And for that to exist, they have to agree. They have to be the same thing. So if these two things don't agree with each other, if they're not equal, then this doesn't exist. The third case is a weird one, and we're just kind of throwing it in for completeness' sake. A function like cosine of 1 over x. So it's a weird looking graph, and it's even weirder the farther you zoom in. Kind of think about why. If x is a really tiny decimal, like if x is 0.01, then 1 over 0.01 is 100. But if x is like 0.02, then 1 over 0.02 is 50. So we're like jumping from cosine of 100 to cosine of 50 in the space of 0.01. I hope that makes sense. It really doesn't matter. Just know that as you get closer to 0 here, as these numbers get smaller and smaller, this function becomes incredibly chaotic. It's almost like a fractal. The more you zoom in on it, there are patterns, but they're completely unpredictable. So obviously f of 0 is undefined. That's one thing, but that doesn't mean that the limit's not there, right? F of 0 has a 1 over 0 in it, so that's no good. The reason the limit's not there is because of that chaotic, erratic behavior where it's just jumping back and forth extremely fast from 1 to -1 and whatever else in the middle. So it's a weird case. We can't look at it. The more you zoom in on it, the more chaotic it is. So we literally just have no way of knowing what's happening right near 0, because the closer you get, the more it jumps around. So I don't know how much you're really going to see that, but those are the three cases where you just would say that the limit doesn't exist. If it's either an asymptote or a split in the graph or something like this where we just have like utter chaos happening near a certain point and we just can't even say what it even would be if it did exist. So here's an example of a problem you will definitely have to do on some sort of exam or quiz coming soon. It's just a big weird graph with a bunch of stuff in it that I'm going to ask you a bunch of questions about what various limits are, if they even exist. So you look at the graph and you say, okay, f of 0, remember if I have a open dot versus a filled in dot, that means the function is not defined here. So the way it appears is that f of 0 just is undefined or doesn't exist. So either one of those things would be fine and correct to say. However, the limit as x approaches 0 of f of x. So the limit doesn't care that the function is not defined, right? The limit only cares what happens to either side of it. And it sure looks like if you're coming to x equals 0 from either direction, that the function is jumping over the number 2. So just because the function is not defined there doesn't mean that the limit's not. If there's a hole, the limit is defined. So the limit would be 2. So f of 3, again, you just have to kind of understand this graph notation. F of 3 appears to be 3. Why? Because we have a filled in dot here. So this function does this weird thing where it gets to 3, isn't defined here. It does happen to be defined here, but not here, and then just keeps going from there. So because of the filled in dot, f of 3 is 3. So here's our new one-sided limit notation. Remember, the minus sign means coming from the left. So just ignore the other stuff. Just look at this graph coming from the left, coming to x equals 3. It looks like what the function wants to be there is 1. So the left-handed limit exists, and it's 1. Same deal, coming from the right, so just follow this green curve. It looks like, the way I've drawn it, it's not exact, but the limit does exist coming from the right, and it looks like it's like, can we say 3.7? So if it's not exact, we just say about 3.7, and if you said 3.8, I couldn't mark that wrong. All right, so if we don't specify a direction, that means like a global limit. And for that to exist, it has to be the same coming from either direction. So here it was approaching 2 coming from both ways. At x equals 3, it's approaching a different number coming from either direction. So this limit doesn't exist. And the fact that I defined the function at 3 doesn't matter at all in terms of the limit, right? It didn't affect any of that stuff. So what the function is actually defined to be really doesn't matter as far as the limit's concerned. It only matters as far as continuity is concerned. If we were to fill in a little dot here, we'd make it continuous, but this little dot didn't affect the limit. It's just kind of there to, trick you, I guess. Okay, so if we're coming to x equals 6 from the left, that vertical dotted line there implies an asymptote, in case it wasn't clear that that's what it is. So if you see that, I meant that to be a vertical asymptote. So if it's an asymptote, the easiest thing is just to say that the limit doesn't exist. That would be correct. So, but you could also say that, okay, since it shoots down to negative infinity, if you said equals negative infinity, you would technically be right as well. So it officially doesn't exist, but saying equals negative infinity is just a way of indicating which way it goes. So just use caution. The safest thing is just if you see an asymptote, just say the limit doesn't exist. Okay, same thing with approaching 6 from the right. That's a vertical asymptote. That's how they work. We can't see it, but we're assuming this just shoots up to infinity here. So the limit doesn't exist, or if you said it shoots up to infinity, I couldn't mark that wrong either. Okay, so just using a weird chopped up graph with examples of all the kind of stuff that can happen to make the limit either exist or not, regardless of what the function's actually doing. Oh, and if we said the limit globally coming to 6 of f of x, well, here you have to say it doesn't exist for a number of reasons. A, it's a vertical asymptote, so you can't say it's infinity. But also, if you come from the left, it goes to negative infinity. If you come from the right, it goes to positive infinity. So you wouldn't even say those two aren't equal because infinity is not a number. So the concept of equal doesn't really apply. So all that is to say, it very much doesn't exist there. There's no world in which the limit exists at x equals 6. Okay, so hopefully just visually that gives you an idea of what you're looking at when I just ask you, given a weird chopped up graph, what the limit is. Obviously, at some point we want to do it using, math. And we can do that with the stuff we have. We don't even need to get into what derivatives are. And I mean, I haven't even really told you what calculus is. So to find limits algebraically, there's always a trick. And usually that trick involves simplifying the expression. So we'll start with a familiar example. Okay, we finally get to do some math in this math class. So this is, we've seen that. That was the expression for our curve x squared at the point 1, 1, finding secant lines between 1, 1 and other points. And we found that the slope of the tangent line there, the instantaneous rate of change, was given by this limit. So we made a table and we said, boy, it sure looks like those numbers in that table are getting close to the number 2 from either direction. So I just told you that, and I just said, trust me, let's move on, that this equals 2. So here's how you actually do it. And that, if you're algebra minded, you already kind of know what to do here. So we can't punch in 1 directly, but the goal is generally to get to a place where you can. So if you look at that numerator, if this were a two-way street, I would ask you, what do you want to do to that numerator? What's a thing you can do with it? So I just have to assume that everybody right now is at home screaming, factor it. And that's right. So if you factor the numerator, that's one of those difference of two squares that factors into x plus 1 times x minus 1. And that works because now you can see that something cancels out. And generally that's the goal. Get something to cancel out. So what we're essentially doing is removing the whole when we do that, and then we get to a place where we don't have a 0 over 0. So right here, if you plug 1 in, you're at 0 over 0. Right here, if you plug 1 in, you're still at 0 over 0. But once you cancel that factor out, you can do that, right? You're just dividing, you're just simplifying a fraction. You get this. And now, this is, people have a hard time with this. I don't know why. Now you can do the thing you wanted to do where you literally just punch the number 1 in for x. So this is just called evaluating by direct substitution. You just say, oh, I don't have that problem anymore. If I stick 1 in here for x, I don't have a 0 over 0. What do I have? I have 1 plus 1, which is 2, right? So it's really that easy. Once you get rid of that, your problem, your hole, your thing that's causing it to be 0 over 0, you just stick this number in for x. You just stick 1 in for x, and then you just literally evaluate it directly. 1 plus 1 is 2. So that's easier than looking at a table and just guessing at it, right? If it's something that's easy to simplify, and it's not always going to be that easy, then you just do whatever algebra you have to do to simplify it, and then just stick this number right in here, and it evaluates just like that. Right, so the graph of this, all we really just did is found the hole in it. And if you look at the graph of it, you can tell where the hole is. Now, if you graph it on your calculator, you would not see this. This would be invisible. So that's why we use tables, because it shows up on the table, but it doesn't show up on the calculator, or at least on the graph. But here's a more accurate depiction of the graph. If you look at x equals 1, well, then it's obvious that the hole is at 1, 2. So the limit of this thing as x approaches 1 looks like 2. Okay, let's do another one a lot like that. Limit as x approaches -1 of 2x squared plus 3x plus 1 over x squared minus 2x minus 3. So if you look at it and do some math, and you notice that f of -1 is undefined. You can probably kind of do that in your head. Try sticking -1 into that function and see that it doesn't work. And it doesn't work because you get 0 over 0. So we need to do some math to figure out this limit. If you could just stick -1 in there, you would just do it. So same kind of deal. We have to simplify this in order to evaluate it. And both numerator and denominator are just crying out to be factored. So when you studied rational functions and holes and asymptotes and stuff in an algebra class, I hope you probably did stuff like this. So just factor the top and factor the bottom. That's all you can do, and just see what it looks like. There's only one way to factor these things, and we note that, hey, look, we do have a common factor of x plus 1. If we didn't, then this wouldn't work, and it would be a bad example. So we got something we can cancel, and that means that, okay, we actually can evaluate this limit directly once we do that cancellation. So can't divide out our common factor. We're left with that. And now once again, notice what we did. This was the thing that was causing the 0. Right? This thing was making it be -1 plus 1, which was what made it 0 over 0. So now we got rid of that problem, and now you just plug in. So just take this -1 and stick it in here for x and see what you get. So that's easy. You just do a little arithmetic and you get -1/4. Yeah, the only real way to check that or verify it would be to graph it and look at a table at what happened near x equals -1. You would get an error there, but the numbers in your table should be moving very close to what? -0.25. And that might be a little harder to guess if it's a fraction like this, but you shouldn't guess. You should do the algebra, and then this is just kind of a way to check it. Remember, all we did is we found the hole, so it will have a hole at -1, -1/4. All right, so this one's a little bit trickier. Limit as x approaches 9 of square root of x minus 3 over x minus 9. So it's a different kind of thing, but our problem is always going to be the same. The square root of 9 is 3, so 3 minus 3 over 9 minus 9 is 0 over 0. Right? So there's a hole. If you were to look at the graph of this, you would see, well, you wouldn't see it, but if you looked at the table, there would be a little error at x equals 9. So we want to figure out what that function should be there. So the algebra is different here. We're not factoring, we're rationalizing. Again, I just have to trust that you did this in an algebra class. If not, it's worth a Google. If you, to simplify that numerator, square root of x minus 3, you have to multiply it by square root of x plus 3. And if you're going to do that to the numerator, you also have to do that to the denominator, and that's called conjugating. Square root of x minus 3 and square root of x plus 3 are called conjugates of each other, and the act of multiplying them together is called conjugating. So that's what that looks like when you do that. We got some algebra going on. We're essentially foiling the top. So when you foil this with this, the first term is square root of x times square root of x, which is just x, and that's kind of why this works. For the middle terms, your outer and inner terms, you get a plus 3 times the square root of x minus 3 times the square root of x, right? That's the trick. And then your last term is minus 3. we're going to not multiply out the denominator, and you're going to see why in a second. So that's a thing to keep in mind. Sometimes you don't want to do that, and you'll see why. So the reason conjugating works is because those middle terms cancel out, and all you're left with is the x and the minus 9. So now we have x minus 9 over this mess down here, x minus 9 times square root of x plus 3. So you see why I didn't FOIL it out, because my cancellation is here. If I FOILed it out, I have to then unfoil it and like factor it, which would waste a step. All right, so that move works because we get a common term between the numerator and the denominator. So that cancels out. You're left with just 1 in the numerator and then just that factor of square root of x plus 3 in the denominator. And lo and behold, once again, you see what happened. Now we can evaluate it directly. So we canceled out the factor that was causing the problem. This is the thing that was causing the 0 over 0. You can't plug it in here, but you can plug it in here. So that's what we mean by getting it to a place where you can just evaluate the limit by direct substitution. So you just stick 9 in for x, and it's 1 over the square root of 9 plus 3, which is 1 over 3 plus 3, which is 1/6. Again, you could graph this and look at a table to check it. It would be hard to tell looking at the table that the number that it was converging to was 1/6, because it'd be a decimal. But now that you know it's 1/6, because you did the math, you know, that would really be the only way for you to check these. So just notice the pattern. No matter what, when we try to evaluate these limits where we have these holes, something will always cancel out. And if something doesn't cancel out, you probably made a mistake in the algebra. All right, your turn. So I'm going to have you just go to chapter 1.6 in the book and read about the limit laws. They're not formulas really that you have to memorize or anything. They're super easy to understand and intuitive. They're just properties of limits that make the stuff we have to now do easier. So for me to just list them all out right now would be kind of boring and pointless, and it's just as easy just to read about them and look at some examples. And then I'm going to have you try one of these types of problems because, you know, I've done enough. You should do one. So if you think back to the example of a falling rock and trying to figure out its speed right at 5 seconds, we said, okay, this expression in the parentheses gives its average speed from t seconds to 5 seconds. So this is just delta y over delta x. It's just how far the rock fell divided by how long that took. And the actual instantaneous speed at 5 seconds is given by this limit. Right? We can't plug 5 in right now. And I want you to show that this limit equals 49. So the exact speed of the rock at 5 seconds after we drop it is exactly 49 meters per second. Now we can do that without guessing. And my hint is that you're going to need this property. So this is just one of those limit laws in 1.6. It just says if you have a constant inside of your limit and you want to go ahead and pull it outside, that's fine, if that makes your life easier. So if you've had any kind of calculus and you've done some derivatives, this looks familiar from a rule for derivatives. All those rules are derived directly from these limit rules because a derivative is just a particular kind of limit. So go ahead and do that problem. I'm telling you the answer, so it just takes a little bit of algebra to get there.